Um, so I'll talk about what our role in this project is. And okay. So our overall objectives are to develop the capability for wall-modeled large eddy simulation under the same develop it under the same conditions as a planned experiments, and to use DNS and LES to study boundary layer transition that's induced by tripping. And so the methodology that we'll use is MP Kugel's, our in-house code, which is a methodology to do DNS, LEs, and global stability analysis developed here. For a number of years, we've been doing single grid unstructured grid simulations, but for this project, we'll use an unstructured overset capability that we've been developing over the recent years. And wall modeling, the idea would be to tie it to the experimental data that is being measured. And I'll give you a sense where we are on each of these things. So, like I said, we'll use the overset capability means you attach grids to different bodies and solve the flow on each of these grids, and you couple them, right? So it's a methodology that's typically used for moving bodies, but it's one that's useful for this project, and I'll mention that at the very end. Typically, when it comes to overset methods, the challenges are scaling it up to very large numbers of meshes or processors is difficult. And conservation properties and accuracy are not always maintained. And we've developed a method which addresses these challenges. And these two papers here describe the detail. Now, for this specific project, what we think the overset capability will enable is for us to directly resolve the trip that's going to be used in the experiments on a computational grid. We think we will use the overset capability to resolve the very near wall region in the boundary layer, as well as the wake and large scale vortices, because that's one thing that's challenging. As Joe pointed out in his introductory slide, you can imagine in the attached regions, getting that near wall region that is responsible for CF, as well as at the higher angles, the vortices that shed and then potentially wake. And because we are scalable, these calculations will be large. And so that's something we can handle. I wanted to show you some examples, related examples, in the next few slides. This slide shows you an application of the overset capability to do LES of sub-off, right? This is at a REL of 1.1 million. And these are all overset calculations. So this is, let me turn the pointer on here. That's helpful. Yeah, so this here is the U velocity, this is pressure. And if you just go through the figures, this figure here in the middle is the pressure coefficient on the surface. And the pressure coefficient here is compared to experiments at Card Rock done by Wang at a higher Reynolds number of 12 million. Right? But because the flow is attached, you expect CP to agree, and indeed it does. The figure on the left, and this is what's important, right, from an LES standpoint, is this is CF compared again to the Wang et al. Data, which is now scaled down using zero pressure gradient scaling, right? And so this is CF from the LES compared to experiment. And these are two stations from a different experiment done by Jimenez et al. So these are profiles in the wake. One is at 3D and one is at 60. We are the solid line, they are the symbols. And this is, right, another measure that you're getting the drag right. Okay. This slide is an example of using the overset capability to resolve the trip. Okay. So in this case, this is sub-off, and it's wall resolved overset LES. REL is 1.1 million. And the tripwire geometry is that the tripwire geometry is the same as what was used in the Jimenez et al. Experiments, which did the wake measurements. And so if you look at this figure here, this little white region is the trip, and this is an overset grid that's wrapped around it, and this is sort of the overlap region. If you look at this figure on the bottom, this is the streamwise velocity, and this sort of band here is the trip. In this case, it was just a circular ring, and you can see the flow transition downstream. And there are two figures here that I'm showing, one for CP, one for CF. And the CP is again compared to Jimenez, right? And there are two curves actually, which you can kind of see, a red and a blue here. One of them resolves the trip. The other is a calculation where we model the trip with a blowing condition. And the intent of this curve, of this plot, is to show that both simulations basically fall on top of each other. We've been looking, so these are calculations or exploratory sort of calculations for the 6:1 spheroid, that is for this effort. So this is a spheroid, this is a mesh about it. And this here is the same trip, right? It's just a ring circular trip that's wrapped around the spheroid. And this is the mesh that resolves it. And we just wanted to see what would happen and to get a feel for what the challenges are that's posed by such, what the challenges are. And so this is, and here I'm showing you two figures that are part of this exploration. One of them has the tripwire at 0.2 L, the other has it at 0.1 L. And these contours here are a lambda 2 isosurface colored by velocity. The Reynolds number here, REL, is 25 million based on length, because that sort of falls within the range of where we want to go. The angle of attack is 20 degrees. And in a nutshell, basically this leading edge region, as Joe alluded to, is actually, it's extremely interesting and quite challenging. And these are some of the challenges. One is when you're high RE, the laminar region here, I mean, that boundary layer is quite thin, and then it accelerates, right? And the radius of curvature for the spheroid is small, so your suction at the leading edge is high. And so this adverse pressure gradient here is high. And of course and then you have, as a result at alpha, you have this cross flow. So large curvature, pressure gradient at the leading edge, 3D boundary layer. And so these combine in terms of the instability of the flow here. You have both TS as well as cross flow instabilities. And so the flow, what you see, and both these pictures show that, is that in our calculations, you see sort of the flow wanting to transition upstream of the trip on the leeward side. And this region here at this angle of attack corresponds to the onset of the adverse pressure gradient region on the leeward side. The flow here is quite sensitive, at least in the calculations that we performed so far, to mesh resolution, to basically, it's quite sensitive. Let me just say that. So what you spoke to, those measurements here, I think would be quite useful in terms of getting a handle on what happens here. This here is a geometry of in Dave's email. Dave, you had mentioned the trips that you were considering, right? 36 of them, pegs, 0.8 millimeters, 1 millimeter diameter. And so we just went, this was on Monday, that evening that you sent your email. We just wanted to see if we could handle them in the geometry. And I thought I'd just show you a result. So these are the peg trips that you mentioned in your email. And these are 3 pictures where we basically mesh them up. We haven't run flow through it as yet, but just mesh them up to show you what's possible. This is a zoom out, right? You zoom, where you just see a mesh. You zoom in and you see these little bands, right? You're zooming in some, each of these are your 36 pegs, right? And then you zoom in some more, and each of those little things are the pegs. And so what we hope to do is to explore directly putting this in the calculation and seeing how it trips the flow, okay, to connect to what you're considering. I'll quickly go through the wall model LES capabilities, which exist in the code, right? So in wall modeling, you solve the LES equations of the modified wall BC, you apply Norman BCs on the wall, and right now we use the law of the wall to obtain mean wall shear stress. And a typical grid resolves the top 80% of the boundary layer. The grid spacing scale with delta and not in plus units, right? And we tested this. I'll just show you a couple for turbulent channel flow at Reynolds numbers up to 5,200 and actually even 20,000. At 20,000, we couldn't compare to data, so I won't show you here. Boundary layers we've done at Reynolds numbers up to 10,000 and higher, as well as axisymmetric boundary layers at varying RE theta with this sort of an approach. And this, for example, is channel flow, RE tau 2000, 5,200, where we are comparing to DNS data of Hoyas and Jimenez, right, in terms of, and what I'm just showing you is their ability to get the friction right, and therefore the profiles. This is a boundary layer at 2 stations, RE theta 2500 and 3000, okay, and this is the comparison. And this is sub-off. And wall modeled LES or sub-off and this is done at, actually we've just done 3 Reynolds numbers. One is REL of 1.1, 12, and one is 67 million. And here I'm just comparing CPCF to the Wang et al. Data, which was 12 million. And you can see that CP for all three cases looks okay. There are differences in the Stern region, as you might expect, right? But the 12 million shows reasonable good agreement with the 12 million experiments. And this is CF at Reynolds numbers, at the three different Reynolds numbers. And the agreement is encouraging, but still there is room for improvement, right? And so that's one of the things that we hope to, from a fundamental standpoint, address within this effort. And lastly, I wanted to tell you about the stability analysis that we have in mind, which is, and we with that we will use to look at the tripping and the whole transition sort of issue. So we can basically do linear stability analysis for 3D base flows within MP Kugels, right? And so we actually solve the linear equations. That really is all that this equation here is. We don't take the nonlinear equation and apply a small disturbance. We can solve the adjoint equations, right? So this is a momentum adjoint that gives you information on flow sensitivity. Where is it most sensitive to perturbations? And then we can solve the optimal perturbation equation. So if you impose some time frame, some time scale, what disturbances are grow most on that time scale? Yeah, and these three arrows here just say that each of these statements boils down to a different eigenvalue problem. And so basically we can do this within MP Kugels right now. And I just wanted to show you its application in a couple of slides, for example, to a jet and cross flow. So this is a jet and cross flow. And the main thing I wanted to say is that we can reproduce spectra associated with stability that are measured in experiments. So in these experiments, basically spectra were measured at these three stations along the leading edge shear layer of this jet. These are the experimental spectra at 4 stations. This is MP Kugels. Yeah, and you see basically good agreement here. When you take the mean flow and apply stability analysis, this is at 2 velocity ratios. The dashed lines here, so this is growth rate as a function of Strouhal number. The dashed line are the peaks that are measured in the experiment. And these things here are the most unstable modes as given by the linear stability analysis. And we were very happy to see this close correspondence. And furthermore, the stability analysis you see for the higher velocity ratio gives you this mode here. This corresponds to the downstream shear layer. And there were no measurements made in the downstream shear layer, but the simulations basically helped reveal that. And I wanted to conclude with one last plot, which basically compares the eigenmodes, right? The intent of this slide is to show you the relevance of linear stability analysis to these complex turbulent flows even. These are the eigenmodes at your 2 velocity ratios. And these here are modes obtained from DMD of the full nonlinear simulations. So you do DNS, then you extract at this frequency, you extract the most dynamic mode. Its shape looks like this. And you see the close correspondence between the linear stability mode and what you see from the actual DNS. So these are the sorts of tools and perspectives that we'd like to bring to this problem. And